All right, welcome back. We are continuing our discussion of power series. And in this video for section 6.1, we're going to delve in a little bit deeper. We're going to see if we can actually come up with a specific power series representation for a specific function. And we are going to use what we know about the geometric series. If you'll recall, that our geometric series always converges or always has a sum a over 1 minus r as long as the absolute value of r is less than 1. Okay, so how are we going to use this? Well, specifically, we're going to let the first term be 1, and we're going to let r equals x. And let's see how that changes things. Well, if that's the case, we have that, then this sum a over 1 minus r becomes 1 over 1 minus x. And so the advantage of this is this helps us it helps us to determine a power function or a power series for any function that has a form that's similar to 1 over 1 minus x. Because if we did, then that would be the series from n equals 0 to infinity of x to the n, which we know converges for some values of x, not all. It converges for all values, absolute value of x less than 1, or values of x between -1 and +1. So any function that has the form 1 over 1 minus x, or some form similar to that, we can use the geometric power series representation. So let's see how this works. Now, example 2, part A, notice we have a function. It's not exactly the same as what we're talking about here. Remember, we're using f of x equals 1 over 1 minus x, that form. So we have to get this, we have to make it look like what we just talked about. So, one thing we could do is we could move the 2x squared that's in the numerator out front. So if we move that out front, we're left with 1 over 1 plus x cubed. And then, remember, it's 1 over 1 minus x, so we need a minus there. So we could also rewrite this. We could say 2x squared times 1 over 1 minus a minus x cubed. And now it looks like exactly what we just talked about. So we still have the 2x squared on the front, but the second part, this part, matches here. As long as instead of x, we treat it as negative x cubed. Well, how does that change things? Well, the x in our function matches with the x in our power series. So that means this is times a geometric power series, but instead of x to the n, so instead of x to the n, we're going to have negative x cubed to the n. Okay? And that's because we have negative x cubed here instead of x. And so then it's just a matter of algebra after that. So this is the same as 2x squared times the sum of -1 to the n times x to the 3n. Now, how do we get that? Let's go ahead and do a little math on the side. Just make sure you're okay with that. So we have, again, negative x, excuse me. We have negative x cubed to the n. This is the same as -1 times x cubed to the n, which is the same as -1 to the n times x cubed to the n, which is the same as -1 to the n times x to the 3n. And so at that point, we just have one more thing. So this x squared can go back in. So we have 2 times the sum, n equals 0 to infinity, of -1 to the n times x to the 3n times x squared. And using the power rule, or the product rule, excuse me, of exponents, we have -1 to the n times x to the 3n plus 2. And you just need to get in the habit of combining exponents like that, where you add the powers. All right, so our original function, our f of x, that was equal to 2x squared over 1 plus x cubed, this is a power series representation. Now, it's not true for all values of x. It's only true for a certain number of values. Remember, our original power series is geometric, so it's only convergent for absolute value of x less than 1, or in this case, it's only convergent for absolute value of -x cubed less than 1, or absolute value of x cubed is less than 1, or just x is less than 1. So that means we can say, because we have that, we can say that our interval of convergence, is -1 to +1, and our r is equal to 1. And there you go. Okay, let's go ahead and do one more example. So again here, we want to get our h of x here to look like the function 1 over 1 minus x, which we don't have at this point, but with a little bit of manipulation, we can definitely get to that. So again, we can pull the x out in front, which leaves us 1 over 5 minus x. And we really need this 5 here to become a 1. And so let's pull the 5 out as well. So this is, rather than, let's erase this, and let's pull out x over 5. Now if we pull out x over 5, we're left with 1 over 1 minus, and then what would the second part look like? It would have to be x over 5, right? Because if we were to distribute the 5 back in here, 5 times 1 is 5, and 5 times x over 5 is x. So we have x over 5 times the sum, n equals 0, because the 1 over 1 minus x over 5 is our geometric power series, except instead of x to the n, it's x over 5 to the n, right? That is going to be equal, so the 1 over 1 minus x over 5 is the same as this power series for, we can say for what values of x? For absolute value of x over 5 is less than 1. That's our r, right? As long as that r is less than 1, it's going to converge. And so go ahead and simplify here. We have x over 5, then we have x to the n over 5 to the n. And actually, let's, instead of doing that, why don't we, just looking at it, notice they both have x over 5. This is x over 5 out front, x over 5 to the n. So couldn't we just rewrite this as x over 5 to the n plus 1? So there we have a power series representation. This is equal to h of x. And it's equal to it for, if we go ahead and solve here, we can say that x minus 5 less than 1 implies that absolute value of x is less than 5 if we multiply both sides by 5, right? So that means our radius of convergence is going to be 5, and our interval of convergence is going to be -5 to 5, because this means the x is between -5 and +5. So interval of convergence, -5 to 5. Radius of convergence, 5. And that's our answer, and that's going to finish it up for section 6.1. I'll see you in the next video, next section. Thank you.